And now for our second section on the development of the Lebesgue integral and dealing with what I've called the class 2 functions. The title of section 4.3 is the Lebesgue integral of a measurable non-negative function. So what we'll do in this section is drop the restrictions from the previous section of boundedness. We had bounded functions on sets of finite measure. So we're going to abandon the boundedness part, but we're going to consider in this section only non-negative functions and maybe let them take on the value infinity. So they'll be extended real valued functions. And this is what I've called class 2 of functions. So we've lost the boundedness, so there's an opportunity for divergence, opportunity for integrals as well as functions to take on the value, quote unquote, value infinity. But we won't have to worry in this section about any infinity minus infinity things popping up in computations because we got no subtraction. Nothing is negative in this section, so there isn't any subtraction to be concerned with. This will be a driving force in class 3 when we look at the next section. So to get things started, we're going to consider some functions that, strictly speaking, they'll belong in this class 2, but in a sense, they're effectively in class 1. I want to define the integrals of our class 2 functions, non-negative functions, in terms of the class 1 functions, the functions involving all the bounded stuff. So as a definition, a measurable function f on a set E is a finite support if there's an E sub 0, a subset of E, that E sub 0 set having finite measure, and f is identically equal to 0 on the complement of E sub 0, that is on set E, set minus E sub 0. The support of f is the set of x values where the function is non-zero. So if we have a non-negative function of finite support, this is what we'll deal with, we've effectively got a function that's defined on a set of finite measure. Well, off of that set of finite measure, we've got the function taking on the value 0 off of that set. So in class 1, we considered bounded functions on sets of finite measure. We're going to drop this condition on the finiteness of the measure of a set over which we integrate. So set E will simply be a measurable set and we'll integrate over set E, but we'll impose a condition of boundedness and finite support in order to create some functions that, strictly speaking, are in class 2, but they're effectively in class 1. So we'll have bounded functions of finite support. The only thing that keeps them from being class 1 functions is maybe they're defined on sets of infinite measure, but they're 0 except on a set of finite measure. So to be rigorous and formal about this, we do need to define the integral, the Lebesgue integral of such functions. So let f be a bounded measurable function on E which has finite support. Say it's 0 on E set minus E sub 0, where the measure of E sub 0 is finite. And that's what finite support is. Then define the integral over E of function f to be the integral over E sub 0 of function f. Okay, what's happening here is on the right-hand side, E sub 0 has finite measure. So on the right-hand side, this is defined from the previous section. This particular integral concerns on set E sub 0 a bounded function on a set of finite measure. So the right-hand side, that's class 1 functions and class 1 integrals, bounded functions on set of bounded measure. Now, this function f is 0 off of that set E sub 0, that is on E set minus E sub 0, the function is 0. So it's reasonable to define, and it's a definition, so we take it as is given, but it makes sense. And the only difference between these integrals is on the left-hand side, we've got a function that's 0 on maybe a big set, or maybe even a set of infinite measure. So it's reasonable to ignore wherever the function is 0 in terms of integrals. And that's the motivation for this definition. But it is a definition and it deals with a new setting. The newness coming in the fact right there that that set E might have infinite measure. If it has finite measure, then we're back in class 1 and we're back in the previous section. We're still keeping F bounded and we're still keeping it 0 except on a set of finite measure. But where it's 0 might be a set of infinite measure. The fact that set E may have infinite measure means, strictly speaking, can't do this, can't deduce this from the previous section. So we have to take it as a definition. One of the exercises, problem 418, you're asked to verify that this definition is proper, that is, that the integral is well defined. In other words, we've taken the set E sub 0 in a non-specific way. It's got finite measure and the function is 0 off of that set of finite measure. Well, there's a bunch of sets potentially which have finite measure and the function is 0 off of those sets of finite measure. I could include additional things, not too many things. I need to keep that E sub 0 with measure finite. But if I find one candidate E sub 0, I could potentially add some points to it, just as long as I keep the measure finite. And the function will still be 0 outside of that set. So this is potentially not well defined. It shouldn't depend on how set E sub 0 is chosen. And that's what you're asked to show in problem 4.18. Okay. So that was, arguably that was class 1A of functions. I didn't write this out like that. But we're now in a position to define the definite integral for class 2 functions, for non-negative functions, using class 1 functions. Okay, strictly speaking, we're using the functions that are described in this definition up here. So those functions, I want to say they're effectively in class 1. So we're still effectively using class 1 functions to define integrals of class 2 functions. So for f, a non-negative measurable function on E, define the integral of f over E as integral of f over E, non-negative function, the supremum of the integral over E of h such that h is bounded, measurable, of finite support, and h is less than or equal to f. And keep it non-negative. Everything in this section is non-negative. It's a definition, so you can't argue with it. But this looks a lot like how we define lower Riemann integrals in the previous section. Here we're defining the integral straight up with no upper or lower stuff. One reason for that is f is a non-negative function. Well, it might not be bounded, but if it is bounded, then let's see. I'd like to try to force it into class 1. I still have the measure of set E potentially causing problems, but nobody said this function's bounded. They said it's non-negative. So I couldn't find a bounded h that's greater than or equal to f, potentially, because f itself might not be bounded. But I can always find bounded functions less than or equal to. All right, so there's the definition, and it is indeed defining the definite integral for these class 2 functions, non-negative functions, well, non-negative measurable functions. Of course, we're only dealing with measurable functions when dealing with the integration. But this gives us the definition of this class 2 of functions in terms of functions in class 1, effectively in class 1, in terms of these functions mentioned above. Bounded measurable functions of finite support. Okay, they're finite support, so they're not defined on sets of finite measure, but the only place they ain't 0 is on sets of finite measure. So they are effectively in class 1. And we know how to integrate them to be very clean with the logic by this definition given at the top. So we're effectively defining an integral of the function in the second class in terms of integrals in the functions in the first class. And we defined integrals of functions in the first class in terms of integrals of functions in class 0, the simple functions. Again, this being rather informal, and I made up all this class 1, 0, 1, and 2, and 3 stuff myself, but it gives you an idea of how we built things up in layers. Okay, a couple little technical things here that have bugged me over the years of teaching this class. It might appear that when we integrate a function that is infinity on a set of measure 0, we're using some sort of idea that 0 times infinity equals 0, because we're now allowing these functions to be extended real valued functions, so they can take the value infinity on. They'll usually only do that on sets of measure 0 for some reasons we'll see at the tail end of this section. But we ain't doing that. There is no 0 times infinity. What is 0 times infinity? Well, calculus 1, it's an indeterminate form of a limit. So this isn't arithmetic. We're not doing this. This doesn't make sense. We've hidden any such problem in the stages of development of the definitions of integrals. Hidden. It comes out from limit procedures. It comes out from the definitions of the integrals. In problem 417, it's to be shown that if f takes the value infinity on a set E and the measure of that set E equals 0, then the integral is 0. That's what occurs. And that's established using the previous definition, the definition at the top of this page. So it comes out of the definitions that specifically a function that's infinity on a set of measure 0 has an integral which is 0. It comes out of the definitions. It doesn't come from some weird thing like this. I've been dealing with this Royden book for literally decades. The third edition, I say quite surprisingly, the third edition of Royden's Real Analysis states, quoting from page 36 of the third edition, these notes are based on the fourth edition, the operation infinity minus infinity is left undefined, but we shall adopt the arbitrary convention that 0 times infinity equals 0. Bugged me from the first time I encountered it decades ago. This has been cleaned up in the new edition of the book. There's a new co-author, Fitzpatrick. So Royden and Fitzpatrick are the authors now. Royden, talking to you from 2020 here. I'm not sure Halsey Royden's still alive. I don't think he is. If he is, he's not still active. But the book lives on, as often happens with these really good textbooks. But Fitzpatrick's been picked up as a co-author. The third edition has a moderate amount of new stuff over the previous editions of the book. But this must be Fitzpatrick's idea to go through and eliminate this. There's no mention of this, appropriately so. There's no mention of this kind of thing in the fourth edition of the book. Yeah, the theory's taken care of in terms of the definitions. So none of this stuff here. Okay, another setting where we might worry about some 0 times infinity stuff is, to contrast this with what we were just talking about here, we're discussing a function which is infinity on a set of measure 0. Well, we could sort of swap the roles of those two and have a function which is 0 on a set of infinite measure. Another setting in which we might encounter this involves functions that are identically 0 on sets of infinite measure. I might even try to interpret that as a simple function. We considered simple functions when we were dealing with class 0 as defined on, I think we had them defined on bounded sets. We certainly applied them to bounded sets. This definition given above on the previous page will give us that if f is 0 on a measurable set E with infinite measure, then the integral is 0. It'll come out of the very definition of what we have. This is definitely a function of finite support. It's never positive, so I can take any set I like to indicate the set on which we have the function identically 0 on the complement, right? It's 0 everywhere. So this will follow that when the function is identically 0, then the integral is 0, even if the measure of the set is infinity, which doesn't seem at all surprising. Here's an argument of that, also put together in terms of dealing with functions of finite support. The only kind of finite support function we'd have that's less than or 0 is less than or equal to that finite support bounded function less than or equal to f. The only such functions are h equals 0 themselves. And hey, when h is 0 is a bounded function on a set of finite measure, then the integral of the h is 0. So the integrals, when we take the soups from the definition, we'll get an integral of 0. So a couple of weird things involving the extended real numbers. Yeah, we get behaviors that would be expected as spelled out in those two results. Okay, so let's move on to doing something a touch more productive. If f is a non-negative function defined on set E, I'm not saying measurable every time we encounter these things, but of course the sets are measurable and the functions are measurable. F equals 0 almost everywhere on that set, then certainly the integral will be 0. We want to show the converse of that. So functions which are 0, well, almost everywhere, we'll have integrals which are 0. Does that mean if we have non-negative functions which have integrals of 0, then those functions must be 0 almost everywhere? It does, and we'll prove that using the following. Lebesche's inequality says that f be a non-negative measurable function on set E, so non-negative, then for any lambda strictly greater than 0, the measure of the set of x values such that f of x is greater than or equal to lambda is less than or equal to 1 over lambda times the integral over E of f. Okay, we'll go through the proof of that. Let's convince ourselves it makes sense first, though. I claim Lebesche's inequality isn't surprising if you'll cross-multiply. Cross-multiply, take the lambda to the left-hand side, you get lambda times the measure of the set of x values where the function is greater than or equal to lambda is less than or equal to the integral over E of f. Think of this as a rectangle, kind of like a Riemann sums type rectangle. Although the base is actually a measurable set, so, you know, the idea of a rectangle is taking some liberties there. But look at this picture. Okay, here's a function f. It's non-negative. Here's a value lambda. And we're looking at the x values where the function is greater than or equal to lambda. So that'd give this bunch of x values down here. It's in red, if you can tell, red along the x-axis. This bunch of x values, the function's above there, and this bunch of x values. So this is a piece along the axis in red. This is a piece of set E. These x values are in set E, and these x values are in set E. Now, what we're saying is lambda times the measure of E, okay, that would be the bit of, I don't want to say, lambda times the measure of E would be the sum of this rectangle plus this rectangle plus this rectangle, chopping them off with a height of lambda. That's what lambda times the measure of E is. And the claim was that's less than or equal to the integral of f. All right, integral over E of f. We're actually looking at my notation's a little bit off here. We're looking at a subset of that set E. The subset we're looking at is the stuff in red. But what we're claiming then is the area of this rectangle plus this rectangle plus this rectangle is less than or equal to the area under F over set E, which it is. In fact, just this little piece here, this little piece here under the function, and this little piece here under the function. There's potentially other things contributed as well. But this is a picture to illustrate the fact that, Chebyshev's inequality, when I see how to interpret it in terms of areas, okay, wink on the areas, right? This is a nice little continuous function, but still I think it's useful to look at this one as a motivation. Then the Chebyshev inequality makes pretty good sense. Let's go through proof of the Chebyshev inequality. Okay, there's the claim. And as I said, yeah, we're actually integrating f over the entirety of set E, and the measure of the stuff I drew in red is actually a subset of that. It's where the function is greater than or equal to lambda. Okay. Define E sub lambda to be these sets here. That is a set of x values where f of x is greater than or equal to lambda. And we're going to have to consider a couple of cases. Suppose the measure of that set is infinite. Then we'll need to show the integral is infinite. All right, for n a natural number, define E sub lambda comma n to be E sub lambda intersect negative n to n. That's a set of finite measure. These E sub lambda comma n's are sets of finite measure. So what you've done is you've taken this E sub lambda set and you've chopped it off. You've intersected it with the interval negative n to n. So if it happened to be unbounded, you cut the n's off at value value n, negative n to n. Okay, so, well, E sub lambda comma n, it's a subset of this interval, so it's going to have finite measure. And we're going to define psi sub n to be lambda times the characteristic function on that E sub lambda comma n. So we're taking the value lambda and a characteristic function on this set of finite measure. And this has some representation in the picture we were looking at as well. So this psi sub n, it's a bounded function, right? It only takes on two values, lambda and 0, because that's the two values a characteristic function take on are 1 and 0. So we get lambda and 0 out. So it's definitely a bounded function. It's a measurable function because all the sets we're dealing with are measurable. And it's a finite support. That is, it's non-zero on a set of finite measure. The set on which it is non-zero is a subset of the interval negative n to n. Right, characteristic function on that set. So we do have finite support for these psi sub n's. Okay, those we know how to integrate. So when we integrate the psi sub n function, we'll simply get the value times the measure of the set. The value of the function is lambda and 0 times the measure of the set on which the function takes on these values, and it's actually this E sub lambda comma n to be specific. We've got psi sub n to be greater than or equal to 0. It's either 0 or lambda. And we've got psi sub n to be less than or equal to f. Where f is greater than or equal to lambda, we've got the psi sub n's being either lambda or 0. Where the function f may not be greater than or equal to lambda, we've got the psi sub n being 0. And remember, f was non-negative. So we do have this occurring throughout set E. Psi sub n is less than or equal to f and non-negative. So we've said that E sub lambda here has infinite measure in this case. So infinity is the measure of that set. We need to look at some of the very preliminary stuff about extended real numbers. I multiply in this setting, lambda is greater than 0. So this is going to produce an infinity out when we have lambda times the measure of that set. Extended real number or arithmetic, which we do with great caution, but that's how this was defined. All right. If we'll take a limit as n approaches infinity, and what we did to create these E sub lambda comma n's is we took the E sub lambda set up there and we cut the ends off at negative n and n. Well, when n gets bigger, the intersection we're doing here intersects with larger and larger intervals. And if we'll take a limit as n approaches infinity, the E sub lambda n will equal E sub lambda. These are nested sets, these E sub lambda n's, treating n as the index. That forms a increasing sequence of sets. So we can talk about limits of that sequence of sets. And we can deal with continuity of measure. So let's see, the measure of E sub lambda is the limit as n approaches infinity of the measure of E sub lambda comma n. The limit as n approaches infinity in these sets produces the E sub lambda set. Limit of this sequence of sets is that set. So the measure of that set is the limit of the measures of those sets. We've taken the limit out of the measure, continuity of measure. Okay, measure of E sub lambda n, you can actually pull the lambda back inside that limit if you like. We have lambda times the measure of this set. Hey, lambda times the measure of that set was the integral over E of psi sub n. So we'll make that substitution. We've still got the limit. Okay, the psi sub n's were all less than or equal to f. And let's see, let's get this inequality correct here. So what's going on is we would define the integral over E of f to be a sup over bounded measurable functions of finite support integrated over set E. So we take the integral over E of bounded measurable functions of finite support, of which psi sub n, these psi sub n's are some, and then we take a sup over that. So what we've got on the right-hand side is a supremum over all functions, which are bounded, measurable, of finite support, and less than or equal to f. That was the definition of these symbols. So the integral over E of psi sub n would be less than or equal to the integral over E of f for all n. So you take a limit, and then we get that same bound. So it's pretty subtle. I'm really attempted to use some sort of monotonicity here because I've got the psi sub n's less than or equal to f. Well, the problem with that is we don't know we got monotonicity in this setting. We do when we'll prove it, but we don't have it yet. So it's actually the definition of integral of this class 2 function, this non-negative function, that gives us this inequality. So we've got infinity is less than or equal to the integral, so the integral must be infinite because it must be reduction to equalities here. So the integral is infinite and the claim holds, right? We've got the measure to be infinite, and on the right-hand side we'll have infinity as well. So we do have the inequality satisfied in the event that this E sub lambda set has infinite measure. What if it has finite measure? Okay, suppose the measure of E sub lambda is less than infinity. It's finite. Define H to be lambda times a characteristic function on E sub lambda. All right, that's a bounded measurable function of finite support. Yeah, it's, let's see, a function that only takes on two values, 0 and lambda, so it's certainly bounded. It's a finite support. The only place it's non-zero is on E sub lambda, and E sub lambda has finite measure, so we're in business there. H is itself non-negative and less than or equal to f, right? That's because if H ain't 0, then it's lambda, and the places where H is lambda are places where the function f is greater than or equal to lambda. So this is the function value on, or for such x values on the set E sub lambda. And we get the inequality f of x is greater than or equal to h on those sets. So we've got indeed, h is non-negative and greater than or equal to 0 and less than or equal to f, and that holds throughout set E. So again, by the definition of integral, h is a particular bounded measurable function of finite support. So the integral over E of f is defined to be the supremum over all bounded measurable functions of finite support when integrated. This is a particular one. Well, a particular one is less than or equal to the sup, and the integral on the right-hand side is defined as a sup. So again, we get an inequality. It looks like we ought to get it from monotonicity. We don't, because we don't have monotonicity yet. We get it from the definition of the integral over E of f. And we've shown then lambda times the measure of this set here is less than or equal to the integral, and that's what we're trying to show. Divide both sides by lambda to get it specifically to read like this. So Chebyshev's formula, it allows us to prove the following, the converse of what we stated above as mentioned earlier. Let f be a non-negative measurable function on set E. Then the integral over E of f equals 0 if and only if f equals 0 almost everywhere on E. Non-negative functions have integrals of 0 if and only if the function is 0. Well, that makes sense. So I'm going to throw this almost everywhere stuff in there in this setting. But this isn't in the least bit a surprising result. To prove it, we're going to use Chebyshev's inequality. Okay, so if and only if integral of f over E equals 0, if and only if f equals 0 almost everywhere. Remember, f is non-negative. We're now in class 2. Suppose the integral is 0. All right, Chebyshev's inequality then would have us deduce that for any natural number, the measure of the set of x values such that f of x is greater than 1 over n, that must be 0. The function is less than or equal to 1 over this, so be n, times the integral. Chebyshev says, well, the integral is 0, so the measures of all those sets will have to be 0. So we get measures of 0 out on all of these. Continuity of measure again. We're trying to show that f is 0 almost everywhere. So let's look at the measure of the set of x values such that f of x is strictly greater than 0. We're going to show that's measure 0. That would be the measure of, take a union from 1 to infinity, x values such that f of x is greater than 1 over n. If f of x is greater than 0, it's greater than 1 over n for some natural number n. Make n sufficiently large and you'll get this satisfied. Also, this is a nested sequence of sets as well. It's an increasing sequence of sets, if you like. And so this is itself a limit of a sequence of sets. So the limit of the sequence of sets has a measure that's equal to the measure of the limits. This is when I write a union, a countable union like this of an increasing set of functions, that is a limit of that set of functions. We can bring the limit outside of the measure, right? That's the continuity part that we've used right there. Limit came outside of the measure. We observed above, hey, the measure of x such that f of x is greater than 1 over n, all those were 0, so the limit's 0. So the measure of the set of x values where f of x is positive is 0. Well, then f of x must be 0 almost everywhere, because the only place it's positive is on a set of measure 0. Remember, it's not negative, so negative isn't an issue with this. Okay, so if the integral is 0, then the function must be 0 almost everywhere. The non-negative function must be 0 almost everywhere. Let's look at the converse. Suppose f equals 0 almost everywhere on E. Okay, a very reasonable way to approach this would be some sort of additivity, but we don't have that yet either, so we got to go to the definition of integrals. Okay, let phi be a simple function and h a bounded measurable function of finite support, such that 0 is less than or equal to phi, the simple function is less than or equal to h, the bounded measurable function of finite support is less than or equal to f on set E. All right, well now f is 0 almost everywhere. So the phi function must be 0 almost everywhere. So the integral over E of that phi function, that simple function, must be 0, comes from the definition of integral of a simple function. This holds for all phi satisfying this condition. How would you calculate the integral of this h function, this effectively class 1 function? I'd take all simple phi's less than or equal to h, integrate them, and take a sup. Well, the integrals of all the phi's are 0, so the sup is 0. That is, the integral over E of h is 0. Now this holds for all h, a bounded measurable function of finite support, satisfying this inequality. In particular, h is less than or equal to f. How would you define the integral over E of f? By taking a sup over all such h integrals of. Well, the integrals of such h, they're all 0. So the sup is 0. So all that comes out of definitions of integrals. It looks like it's monotonicity, maybe you could get monotonicity out of this inequality here. But the inequality here is going to have to be dealt with. The f function has to be dealt with in terms of the definition of the integral there. But let's do both of them that way. And without directly using monotonicity, we actually can draw the conclusion. So if f is 0 almost everywhere, then the integral is 0. Not in the least bit a surprising result. A little surprising, it takes all this definition stuff to make it tick. It's because we don't know much about class 2 functions just yet. That's what this section's about, though. Okay, so let's build up a little body of knowledge on class 2 functions, that is, non-negative measurable functions. And let's do a linearity and monotonicity result for class 2 functions. We've already seen this twice before, class 0 and class 1. We got one class of functions to go, so you're going to see it a fourth time in the next section. But it says the usual thing that you see in linearity and monotonicity, with an extra little caveat concerning the constants having to be non-negative. This section's about non-negative functions. So in this section, all the functions have got to be non-negative. And let's just go to the proof. The statement is, let f and g be non-negative measurable functions on set E. Then for any alpha greater than 0 and beta greater than 0, the integral of the linear combination of the functions is the linear combination of the integrals. Moreover, is the monotonicity part. If f is less than or equal to g on that set, then the integral over that set of f is less than or equal to the integral over that set of g. Again, this section's about non-negative functions. That's the reason alpha and beta were restricted to be positive. So we get a non-negative integrand when we look at that linear combination. All right, suppose alpha is greater than 0. We'll take care of alpha less than 0 here. Excuse me, there is no alpha less than 0, sorry. For alpha greater than 0, we have the relationship 0 is less than or equal to h is less than or equal to f for any functions on set E. This holds if and only if, well, I could multiply throughout by alpha. Since it's positive, that doesn't affect the inequalities. And we get alpha times 0, or 0 is less than or equal to alpha times h is less than or equal to alpha times f. So this inequality holds if and only if this inequality holds. And if we'll take the integral over E of alpha f, as we've done before, we're going to take care of the scalar multiplication first and the vector addition second. Well, you know, the scalar multiplication and the addition of functions. So very much in the style of approaching things in vector spaces, where you deal with linearity, a bunch of stuff, linear combinations. So we're taking care of the multiplication by a constant thing at this stage. What is the integral over E of alpha f? Well, that'd be the sup of the integral over E of all functions of an appropriate sort. I'm going to take this integrand, let's call it alpha h, to be a bounded function of finite support that's less than or equal to the integrand over here, alpha f. So I'm going to stick an alpha in there, and that affects nothing. As we saw upstairs, it doesn't affect inequalities in particular. We defined integrals of such functions to be soups of integrals of bounded measurable functions of finite support, of which alpha h is one, say. All right, what we're going to do now is say, hey, I can bring the alpha outside of that integral. Says who? Who says you can get the alpha outside of this integral? Why? H is effectively a class 1 function. So we can bring the alpha out front. That could use some justification. But remember, H is effectively class 1. So bring the alpha outside of the integral, justified by H being effectively a class 1 function. And then bring the alpha outside the soup. Okay, no worries in terms of that. So we can bring the alpha outside of the soup. That would leave us with an integral over E of H, bringing the alpha outside of the integral in the soup. Now about this thing over here, if alpha H is bounded to finite support and this holds, well, that's the case if and only if H is bounded to finite support and this holds, as we observed up there. Basically dividing everything inside by alpha doesn't affect the orderings. So the inequalities are preserved. And now we've got, in this soup here, we've got the integral over E of H, where H is a bounded finite support function, less than or equal to F, everything inside is non-negative, and that by definition is the integral over E of F. So we got the alpha out by appealing really to class 1 functions and then appealing to properties of soups. So that's what brings it out, and that takes care of the scalar multiple stuff. Now for the remainder of linearity, for the, I want to call it the vector addition stuff. So what happens when I add two functions together? We're going to add f and g together, taking alpha and beta to be 1, having taken care of the scalar multiple stuff. Okay, so we're going to consider two functions, f and g, two non-negative functions, f and g. Their integrals are defined as soups of integrals of bounded functions of finite support. So let's introduce h and k as bounded measurable functions of finite support for which h is less than or equal to f and k is less than or equal to g. Yeah, and they're always bounded below by 0 because everything is non-negative in this section. Then when we add them together, h plus k, 0 is less than or equal to h plus k is less than or equal to f plus g. Just add corresponding parts together. And h plus k is also a bounded measurable function of finite support. I want to say clearly, of course, if h and k are bounded, then the sum h plus k is bounded. If h and k are of finite support, then the sum is of finite support as well, of course. So h plus k is an appropriate style function. Now, if we'll integrate over e h plus k, I really want to relate that to this stuff over here, and I can. We've got linearity for these effectively class 1 functions. The integral over e of h plus the integral over e of k is the integral of the sum of h and k. By linearity, linearity as applied to class 1, theorem 4.5 in the previous section, applied to these. These are effectively class 1. There's some minor constraints there, some verbiage that needs to be added maybe. But it's linearity from class 1 that gives us the sum of the integrals is the integral of the sums. And that's less than or equal to the integral over e of f plus g. Why is that? Is it because h plus k is less than or equal to f plus g? Is it monotonicity? Well, better not be, because we ain't proved monotonicity yet. It's coming. It's coming in this theorem. No, it's because the integral over e of f plus g is a soup of integrals of functions less than or equal to f plus g, which are bounded in a finite support. An example of one of those functions is h plus k. H plus k is less than or equal to f plus g, and it's bounded of finite support. So this integral is defined as a soup of things like this. This is one of those things in that set of which you take a soup to define the integral on the right. So it's less than or equal to the soup. That's all we're using there. Again, an inequality comes from a soup definition of integrals, not from any kind of monotonicity, because we don't have monotonicity just yet, but we're getting there. All right, I don't want to talk about integrals of h's and k's. I want to talk about integrals of f's and g's. Well, take a soup over all such h of this of both sides of the equation. Take a soup of this over all h such that h is less than or equal to f and bounded in a finite support. Take a soup of the left-hand side. I mean, this doesn't change as h changes, but this does. The soup of this produces the integral of f. Then take a soup over all k less than or equal to g that are bounded and a finite support. And when you take the soup of both sides, this then becomes that integral. Hey, the right-hand side, keep an eye on the price. It's just a number, right? You take soups as h and k changes. This doesn't care. That's just some number. The integral of f plus g over e could be an extended real number, but this doesn't change as you change the h's and k's. These change as you change the h's and k's, and when you take soups, they produce by definition these two integrals. So we get the integral over e of f plus the integral over e of g is less than or equal to the sum of the integrals. There's half your linearity. So we got to reverse it. So we don't want less than or equal to, we want equality in this. Okay, so we'll have to reverse that inequality. It's a touch trickier than you think it might be. All right, to reverse that inequality, let's take L less than or equal to f plus g to be a bounded measurable function of finite support. Define h to be the minimum of f and L. Right, we've got a lot of moving parts going on here. We got three functions. We got the f function, the g function, and the f plus g function. Apparently, I'm enamored with some conversation about the f plus g function initially. Well, I got to get over it and have a conversation that involves, at some stage, f only, and at some stage, g only. So we can talk about these two integrals on the left. But we're taking L to be less than or equal to f plus h, bounded measurable function of finite support. Okay, to motivate the next stuff verbally, we're trying to talk about integrals of f only and integrals of g only. Define h to be the minimum of f and L, and then define k to be L minus h, and do this throughout set E. Okay, can't argue with that. Where we're going with this is something related to f and something related to g. Okay, so let's establish that these h and k's are what we want them to be. They are bounded measurable functions of finite support, and h is less than or equal to f. We want to show that, and k is less than or equal to g. So those are the things we're trying to show. First off, h is bounded, of course. Minimum of f and L, well, L was bounded, and a finite support. So I think h is bounded in finite support. Here we're taking a difference of two bounded functions of finite support. So the difference will be a bounded function of finite support. So first off, h and k are, effectively class 1 functions, bounded measurable functions of finite support. Now we want to establish this inequality stuff. Okay, if x is in E, and if L of x is less than or equal to f of x, So let's see, L of x is less than or equal to f of x. You're going to choose h of x to be the smaller of those two. Well, the smaller of those two will be this one in that case, say. So for such x values, L of x will equal h of x because h of x is the minimum of f of x and L of x. And I know the smaller of the two is L of x. And L of x is less than or equal to f, so we can get this inequality established here. K of x, in this case, K of x is L of x minus h of x. Well, in this case, L of x and h of x are the same, so we're getting 0 out there, and 0 is less than or equal to g. So it's looking good. We've got h of x less than or equal to f of x, and we've got k of x less than or equal to g of x for these x values. That is when L of x is less than or equal to f. Well, what if it ain't? If L of x is greater than or equal to f of x, okay, now that's going to affect how h is chosen. It's chosen to be the smaller of those two. That'll be f of x this time. That is, h of x will equal f of x for such x values. By the way, h of x is then less than or equal to f of x because it equals f of x, so it is less than or equal to for these kind of x values. So what we've established to this point right here is that h of x is less than or equal to f of x throughout set E. About k of x, let's see, that'll be L of x minus h of x. We just observed that h of x equals f of x. So substitute that in here. We'll get L of x minus f of x. And the claim is that's less than or equal to g of x, and here's why. We chose L of x to be less than or equal to f of x plus g of x. Subtract f of x from both sides, and it gives exactly this. So the punchline here is k of x is less than or equal to g of x. So for these kinds of x values, we had the desired behavior. For the only remaining x values where that inequality is reversed, we have the desired behavior. That is, we've got h less than or equal to f, and we've got k less than or equal to g on set E. Okay, what's up now? H and k are bounded measurable functions of finite support that are less than or equal to f and g respectively. All right, that'll allow us to talk about integrals of f individually and integrals of g individually. So h and k are bounded measurable functions of finite support, and we have the desired inequality. So there's a synopsis of what we had. We also have L equals h plus k. That's how we started, actually, was with the L function. By linearity of the integral, theorem 4.5. So that would be linearity in the previous class, what I was calling class 1 functions. Remember, h and k are class 1 functions, effectively. The integral over e of L, that is the integral over e of h plus k, is the integral of h plus the integral of k. So there's where the linearity is being used right there from class 1. We've got that the integral of h is less than or equal to the integral of f because h is less than or equal to f. H is a bounded measurable function of finite support, and the integral of f is defined as a supremum over all such h. So here we're comparing an element of the set to the sup of the set. Well, an element of the set is less than or equal to the sup. And the same thing with the k function and the g function. Again, it ain't monotonicity, it's the definition of these integrals as suprema that's giving the inequality. Okay, so we just showed the integral over e of L is less than or equal to the integral over e of f plus the integral over e of g. We got into this choosing L. How? Let's go back. Previous slide. L was less than or equal to f plus g. It was a bounded measurable function of finite support. So whenever I take any bounded measurable function of finite support less than or equal to f plus g, we get the integral of that function L less than or equal to this, the integral of f plus the integral of g. Well then, what if you take a supremum over all such functions L? That by definition would give the integral of f plus g. L was less than or equal to f plus g. We went through the gymnastics of introducing h and k to get functions that were less than or equal to f and g respectively. But we started with that. So if we take a sup over all such L, this produces the integral of f plus g. And no matter what L is, we've got this upper bound. So when I take sups of both sides, I mean, the right-hand side doesn't change. The left-hand side produces the integral over e of f plus g. And that gives us the remainder of linearity. So we dealt with scalar multiplication first. Second, we had this inequality the other way. And now we've established it. Now we've established it in this direction, leading to an equality. The integral of f plus g equals the integral of f plus the integral of g. So that's what I've called the vector addition part. Then we're set on that part of it. There was the monotonicity part, the moreover part. So we still need to deal with monotonicity. And after this, we know a little bit of stuff about these class 2 functions. We know linearity and monotonicity. For monotonicity, let h be an arbitrary, bounded, measurable function of finite support such that h is less than or equal, 0 is less than or equal to h is less than or equal to f. And we're considering the case, the moreover statement was that f is less than or equal to g. So if h is less than or equal to f and f is less than or equal to g, then certainly h is less than or equal to g, transitivity, eh? So if we'll take the integral over e of g, that's a supremum of all h, the context is not explicitly stated here, all h which are bounded, measurable, and of finite support, and less than or equal to g. So there's a little more to it than what's stated here. But all appropriate h less than or equal to g. This is one of those. So this one element of that set is less than or equal to the sup of that set. So it's that thing again. So that's where that inequality comes from. So if we choose any h, bounded measurable function of finite support less than or equal to f, then we get the integral of that h less than or equal to the integral of g. This is the definition of the integral of g. Well, now take a sup over all such h less than or equal to f of both sides. You've got this number, which is based on h, less than or equal to this number. This number is not based on anything. Function g doesn't change, as it were. Function h does if we take a sup over such h. Take a supremum over all such h, as it says, less than or equal to f. Then this will produce on the left-hand side the integral over e of f, and the right-hand side remains the integral over e of g when you do that supremum stuff. And there's monotonicity of the integral. Okay, so we're getting there, and we know something now about class 2 functions. We know linearity and monotonicity. Mercifully, we won't have to go through this producing of inequalities using the supremum definition anymore, now that we've got the monotonicity. Additivity. We've got an additivity for integrals for class 2 functions, as we had in class 1. This is corollary 4.6 for class 1, where we integrated over A union B. These are disjoint sets. The integral over the union of those two sets is the sum of the integrals over those sets, provided they're disjoint. So additivity, let's go through the proof of that one. It says, let f be a non-negative measurable function on E if A and B are disjoint measurable subsets of E. Then the integral over the disjoint union of f is the integral over A of f plus the integral over B of f. If E sub 0 is a subset of measure 0, then the integral over E of f equals the integral over E set minus E sub 0 of f. If you throw out sets of measure 0, that doesn't affect the values of integrals. All right. First, for E1, a measurable subset of E, we've got the following. The integral over E1 of f by definition is, so we're not done with a definition, but we're done with some inequality applications of it. Supremum of the integral over E sub 1 of h, where h is a bounded measurable set of finite support, and h is less than or equal to f on the set over which we're integrating. Definition of integrals in this class 2. So I want to tweak this a little bit. Let's take the integral over E sub 1 of h and write that as an integral over E h times a characteristic function on E sub 1. When we integrated over a subset, we did so using characteristic functions. It's problem 410. So it was mentioned in the previous section as well. So this integral over E1 of h is the same as this integral over E of h times a characteristic function on E1. So an integral over E1 versus an integral over E. H was a class 1 function, effectively. So problem 4.10 implies that we have this equality here. Taking h to be the same, 0 less than or equal to h less than or equal to f on E1. You know, equivalently, we could replace the h with h times a characteristic function on E1 and say that this holds throughout set E now. So making a shift from E1 up here to set E itself down here and throwing in a characteristic function. All right. This first line is copied from the previous slide. Hey, we've got 0 less than or equal to h times a characteristic function less than or equal to f. Let's put a characteristic function E1 times E1 there. When we choose values from E sub 1, we have this relationship satisfied. When we choose values off of E sub 1, everything in sight 0. So this still holds, and it's these are equivalent. The same collection of functions h. We're doing a soup over all such functions less than or equal to f times a characteristic function on E sub 1. When you do such a soup, that produces by definition an integral of this upper bound thing. And this upper bound thing is f times a characteristic function E sub 1. And these inequalities holding on set E. So what we've shown is an integral over E1 of f. E1, a subset of set E, is the integral over E of f times a characteristic function. This problem 4.10 for this class of functions, for the class 2 of functions, is what we've shown. So there's how you define, well, we've established that it's, don't need it as a definition. We've established that the integral over a subset can be computed using characteristic functions. Now we'll do the same thing we did with linearity in the previous section. With that established, and again, this is problem 4.10 that we used in the previous section, but problem 4.10 was for class 1 functions. We've just established it also holds for class 2 functions. A and B are disjoint. So if we'll take f times a characteristic function on the union, we get f times a characteristic function on A plus f times a characteristic function on B. The exact same observation we made in the previous section. This is actually from here on out, it's the same proof we had from the previous section. So we can express the integral over A union B of f as the integral over E, f times a characteristic function on A union B. It's exactly what we had up here, where E sub 1 is taken to be A union B. We know this function can be written as this linear combination. That's why this shows up right after we've established linearity. We know the integral of the sum is the sum of the integrals. And we know, by what was established up here, that integral of f times a characteristic function over a set equals the integral of f over that set. So this is the integral of f over A. This is the integral of f over B. And that's what was claimed. Let's see, and there was a little bit more. In particular, if E sub 0 is a subset of E of measure 0, then you can throw it out and it doesn't affect the value of the integral. Yeah, piece of cake. E is, what do I want to say, E sub 0 and E set minus E sub 0. Those are disjoint sets. So let's just apply the first part to this. If we integrate over set E of F, set E can be written as E set minus E sub 0 union, disjoint union, E sub 0. E sub 0 is a subset of set E, as it says up here. So we can split this up into these two disjoint sets and use the additivity that we've established. Here, we're integrating over E sub 0, a set of measure 0. We saw above, proposition 4.9, the integral of any function over a set of measure 0 produces a value of 0 for the integral, provided we're integrating over sets of measure 0. We get 0 for integrals. I guess it was maybe non-negative we had to deal with in this section. But applying that to this disappears and you're just left with the rest of it. So the second little claim is really easy once you've got the additivity stuff established. Okay, who's next? Okay, we're interested also in convergence theorems. So as in the previous class of functions, we want a convergence theorem. I'm going to take a little extra step to get to a convergence theorem here and look at some things that don't work to show that we can't just take pointwise convergence in this class of functions and get a convergence theorem. But we're going to start with something called Fotus lemma. So we are interested in convergence theorems. We want one for this class 2 of functions. In class 1, remember we had what was called the bounded convergence theorem because so much stuff was bounded. In this section, everything's going to be non-negative, and we're going to have to impose something more than pointwise convergence of a sequence of functions. So here's a step in that direction, but it's an incomplete step because it doesn't deal with limits, it deals with lim-nths, and it doesn't deal with equality, it deals with an inequality. Fotus lemma says that f sub n be a sequence of non-negative measurable functions on set E. If f sub n approaches f pointwise almost everywhere on E, then the integral of f, that is the integral of the limit function, is less than or equal to the lim-nth of the integrals. All right, I want a convergence theorem. I don't want no lim-nths and I don't want no inequalities. So this ain't a convergence theorem. It's a step in the direction, as the notes say. It's a step in the direction of a convergence theorem, but it's not exactly a convergence theorem. It's half a convergence theorem, I suppose. But it does deal with integrating the limit as compared to integrating the f sub n's in a sequence of functions f sub n that converges to a function f pointwise. So it's certainly relevant to convergence theorems. Let's look at a proof of that one. All right, Fotus lemma. We'll get a surprising amount of mileage out of Fotus lemma. Okay, we just observed the thing about sets of measure 0. Sets of measure 0 don't affect values of integrals. You're told in the hypotheses that we've got this sequence of non-negative measurable functions. Non-negative is our setting, so this deals with class 2 functions. And we've got pointwise almost everywhere convergence. Convergence pointwise almost everywhere. Hey, that set of measure 0 where you may not have pointwise convergence, that ain't going to affect the value of this integral or the value of that integral, as we just saw in theorem 411. So we may as well assume we've got convergence pointwise everywhere. So without loss of generality, we can assume convergence everywhere. Otherwise, I got a set of measure 0 I got to keep up with, and it won't affect anything. So says theorem 4.11. Neither of those integrals, left-hand or right-hand side, are affected by sets of measure 0. So the limit function f, right, the hypotheses where the f sub n's are non-negative measurable functions. There's no hypotheses on the f function other than it's the pointwise limit of these functions. But if all the f sub n's are non-negative, then the limit function will be non-negative. Also, the limit of a sequence of measurable functions is measurable. The pointwise limit of a sequence of measurable functions is measurable. back in chapter 3 when we talked about measurable functions, proposition 3.9, I guess. So f itself is non-negative and measurable, so it does live in class 2 as needed. All right. Let h be a bounded measurable function of finite support for which 0 is less than or equal to h is less than or equal to f on the desired set. So where we're going here, this part shouldn't be surprising. We're going for talking about the integral of f. How is the integral of f defined? As a supremum of the integrals of functions h of this form, bounded measurable functions of finite support that are less than or equal to function f. So we've got to be headed in that direction with the introduction of these h functions. The h functions are bounded, so choose some capital M where the absolute value of h is less than or equal to capital M. They're non-negative, I don't need that absolute value, so actually define e sub 0 to be the x values in E such that h of x is non-zero, such that h of x is greater than 0, given strictly greater than, given the conditions. Okay, that would be, that'd be the support of h. So the measure of that support, the measure of that set must be finite. H is a finite support, that's how we chose it. Let n be a natural number. We're going to establish something in the short run for all n, and then we'll take some limits later. Define h sub n on set E as h sub n is the minimum of h and f sub n. Okay, a minimum of two measurable functions is measurable, proposition 3.8. So h sub n so defined is a measurable function. Also, h sub n is less than or equal to h, because we chose it to be the minimum of these two. It's also less than or equal to f sub n, but it's less than or equal to h, and we know h is less than or equal to m. So h sub n must be less than or equal to h, and in turn less than or equal to m. So we've got this boundedness on the h sub n's. This holding on e sub 0, this is where this is a support of that function. So if it isn't 0, then we still got this bound on it. Off of the set e sub 0 on e set minus e sub 0, the relative complement of the support, h sub n equals 0 because h equals 0, and we're taking the min of these two. There's nothing's negative here. Min of these two will produce zeros there. For every x in set E, we've got h of x less than or equal to f of x, and that's how we chose h right there. H is less than or equal to f on set E, choice of h. F sub n converges to f of x, then we're claiming h sub n of x converges to h. So let's see if we can talk our way through that. Think of it like this. So we've chosen h sub n to be the minimum of these two. As n gets large, these f sub n's are going to get close to f of x. Remember, h and so each of the h sub n's are going to be less than or equal to f sub n. So the h sub n's are less than or equal to the f sub n's. The f sub n's get close to f. Let me give you maybe not a whole bunch of epsilons and deltas, but just a touch more informal argument. The f sub n's get close to f. Well, we know h itself is less than or equal to f. The f sub n's get close to f. Point-wise, I can say eventually the f sub n's are between h and f, if there's even any space there. But eventually, for each x, point-wise, I can get the f sub n's to be between h and f. All right, when that happens, then we're going to have the f sub n's being bigger than h, and so the h sub n's will take on that value h. And this is a point-wise conversation. That is, for all x in the appropriate set E, h sub n of x approaches h of x. But there's a number of little moving parts there to draw that conclusion. but that was an accurate description this time, at least. H sub n approaches h of x. All right, let's apply the bounded convergence theorem to this sequence h sub n. So this was a pointwise convergent sequence of bounded measurable sets of finite support. So bounded measurable sets on sets of finite measure? Well, effectively, yes. So these, again, they're effectively class 1 functions. So if we take let's take the limit of the integrals over E. Remember how the h sub n's were defined. They were 0 off of the set E sub 0. So that's equivalent to taking integrals over E sub 0 of h sub n. Here comes the bounded convergence theorem. Everything's bounded and, well, everything's class 1 functions, let's say, effectively. I can take the limit inside that integral. Take the limit inside that integral. Bounded convergence theorem gives you a limit of the h sub n's. The h sub n's converge to h. So evaluate that limit. We're integrating on E sub 0. That's the support of h. Outside of E sub 0, the h function was 0. So we can also write that as an integral over the whole set E itself of h. And we just showed that the limit as n approaches infinity of the integrals of the h sub n's over E equals the integral of h itself over E. All right, the h sub n's were chosen to be less than or equal to the f sub n's. It was defined in terms of that min deal. So we do get that inequality there. H sub n is bounded in a finite support. So by the definition of integral, so here we are using the definition of integral. I think we could get this with monotonicity. Yeah, we could get this with monotonicity and not have to appeal to the definition of integral. So this could be written up a tiny bit more concisely. But remember, the integral over E of f sub n is the soup of the integrals of all such h sub n's. This is a particular one. So the definition gives the inequality. And yeah, we do have the equipment to throw monotonicity at it at this stage. But we get this inequality established here. So, see, we get the integral over E of h. That's the limit of the integral over E of the h sub n's. That's the outer part of what we had up here. That's what's just established. Now, we know that the integral over E of h sub n is less than or equal to the integral over E of f sub n for all n. So let's take a lim inf of both sides. So I'm taking a lim inf of both sides of this equation. On the right-hand side, we get a lim inf. On the left-hand side, short term, we get a lim inf. But I know from above that that limit exists, I even know its value. So take lim infs as n approaches infinity of both sides here. Lim inf on the right, I don't necessarily know that the limit of these things exist. I know the limit of these exists, we established that. So I can say limit on this side, I'm stuck with a lim inf on that side. And the thing to draw from this inequality is h was chosen to be any bounded function of finite support less than or equal to f. Let's run back and check that. Less than or equal to f. Yeah. All right. H, bounded measurable function of finite support less than or equal to f. Okay, back to where we were. So let's take a supremum over all such h. Take a sup of both sides over h, a bounded measurable function of finite support. Well, there's no h's on the right, so the right doesn't change. But when I do a sup on this side, the sup of such integrals becomes the integral of f itself. Left-hand side, integral of f, right-hand side stays the same, and that's what Fotus' lemma claimed. The integral of the limit function is less than or equal to the lim inf of the integrals. Maybe one additional observation. If you had your choice of what to put on the right-hand side, if you can't put regular old limit, would you rather have lim inf or lim sup? Both of those going to exist. I guess they could be infinite, but both will exist. The limit may not exist. Would you rather have lim inf or lim sup? You'd rather have lim inf. So having lim inf is good news. You're trying to put, it looks like an upper bound on the integral of this limit function. And I want a good idea of what this might be. And if I calculate the integral using this right-hand side, it's an upper bound. I want little upper bounds, right? That gives me a better clue as to what this might be. This is bounded below by 0. I know that because everything's non-negative. But I'm getting an upper bound on this integral. If I take the angle of, if I have my choice, lim sup or lim inf. Well, lim inf is smaller. I like small upper bounds. It more isolates what the value of this could be. Or at least that's my perspective with a little bit of approximation theory that I've done. Now, a couple of things. Well, when the limit does exist, are you still stuck with the inequality? Could it be a strict inequality? Yeah, I got nothing but bad news if we stick with regular old pointwise convergence. We're going to have to add a little something to that. Page 83 of the book gives 2 examples that show the inequality in Fotus lemma can be strict. I like this one, and I got my reasons, and we'll say why here in a sec. Consider the sequence of functions f sub n of x defined to be n times a characteristic function on the interval negative 1 over 2n to positive 1 over 2n. Let's look at a picture. For example, when n equals 1, f sub 1 from negative 1/2 to positive 1/2 takes on the value 1 and 0 outside of that, including the endpoints is how it's set up. N equals 2, negative 1 over 2n, so negative 1/4 to positive 1/4 takes on the value 2 and 0 outside it. N equals 3, negative 1/6 to 1/6 takes on the value 3 and 0 outside that. By the way, this is a poor scale, but the area under these things are always 1. This is 1 unit wide and 1 unit tall. So that's area under this, the integral is 1. The Riemann integral is 1. This is 1/2 wide and 2 tall. Okay, the area under is 1. This is 1/3 wide and 3 units tall. Area under is 1, and so forth. So we're always getting an area of 1. I've described some of this stuff in the past. We encountered something like this before. Think about taking a balloon, blow it up, and tie it off. So the amount of air in it stays the same. If you squeeze it in the middle, then it squirts out on the ends because the volume's preserved. That's kind of what's happening here, except it's a dimension lower. The area under this is 1. And what we're doing when we iterate in the index, we're squeezing it in from the sides. Well, to keep an area of 1 under it, it has to shoot up the y-axis. What do you get out for a limit function? Well, except at 0, eventually this function is going to take on the value 0 and stay there. So the function is 0 everywhere except at 0. At 0, the outputs are f1 of 0, 1, f2 of 0, 2, f3 of 0, 3, f sub k of 0 is k. So the limit is, we approach infinity in the sequence of f of 0 is infinity. So we draw something akin to this, trying to suggest that it took off to infinity. But you've got yourself here a function that's 0 almost everywhere. It's 0 except at this point. So the integral of that function is 0. So what was that? The integral of all these is 1. Here's the limit function. The integral of the limit function is 0. So we've got 1, 1, 1, 1, 1, and 0. We've got the integral of f sub n is always 1, but the integral of f is 0. So stated in terms of integrals instead of pictures, the integral over r of f sub n is, it's always 1, as we just discussed. F sub n approaches a function that's 0 except at 0. At 0, it takes on the extended real number infinity. In other words, the limit is is 0 almost everywhere. So the function, the integral of the function is 0. The integral of the limit function f is 0. So we've got the integral of f is 0. That's strictly less than 1, which is the limit of the integrals, or the limit, if you want to compare it to Fotus' lemma. So what's going on here is, yeah, we got a strict inequality there because the left-hand side is 0 and the right-hand side is 1 for this example. A quick passing comment. Why do they drag us through all this extended real numbered stuff? Well, this is a little bit my opinion. Because they want to take limits of sequences of functions. And, well, limits can certainly be infinite. In Calculus 1, you have infinite limits. You find vertical asymptotes of functions where limits are infinite. You find horizontal asymptotes involving infinite limits as well, or limits as x approaches infinity at least. So the reason they've allowed this extended real numbered stuff to become part of the conversation is because sequences of functions are going to play such a big role. And man, the sequence of functions, they could diverge to infinity. So we're allowing that to happen. But notice, at least in this example, it only happened on a set of measure 0. But that's not a constraint we're putting on extended real valued functions. But the reason they allow infinity as the value of a function, I think, is really because they want to consider sequences. And it's really the limits of the sequences that have to take on values infinity sometimes. So they've set this up using extended real valued functions from the start. The reason I liked this example where you've got 1 under all those functions, it reminds me maybe of probability distributions. Got a supplement to this section called the Dirac delta function, a cautionary tale. I'll prepare a video for that as well. Some of my sorted past when I was trying to do physics, dealing with electricity and magnetism, and something called the Dirac delta function. And some dubious claims made in that setting about these kinds of integrals. Things like, well, it's this limit function, this must be 1 as well, because the limit of all these 1s should give us 1. It gives you 0, as we've established. So you got to be careful with this stuff in terms of limits of sequences of functions. So I say Fotus' lemma, it's sort of half of a convergence theorem. It didn't relate the limit, it related the lim-f. It's not an equality, it's an inequality. Maybe it's not even quite half of 1, but it's some kind of convergence theorem. We can draw a certain conclusion for any sequence of non-negative measurable functions on a set E, not just one that's convergent or almost everywhere convergent. As stated in the generalized Fotus lemma, which is to be proved in problem 4.27, says if f sub n is a sequence of non-negative measurable functions on set E, then the integral of the lim-inf for those functions is less than or equal to the lim-inf of the integrals of those functions. Very much convergence theorem-esque in that it talks about limits of integrals and integrals of limits. Well, lim-infs of integrals and lim-infs of functions in a sequence. And it's not an equality, it's an inequality. But there's a generalization that simply doesn't put any conditions on the f sub n function, like they converge pointwise to something or other. Just says they're class 2 functions, non-negative measurable functions. So about a convergence theorem, we see from that example above at the top of the page that we don't get away with convergence if we just impose pointwise convergence on a sequence of functions. So for class 2, we need something in addition to pointwise convergence. That condition we're going to put on is called monotonicity. We're going to require the function to be monotone increasing. And that monotonicity, along with Fotus' lemma, makes it actually fairly easy to prove our convergence theorem, the monotone convergence theorem. So monotone convergence theorem says, let f sub n be an increasing sequence of non-negative measurable functions. So it's a sequence of class 2 functions, non-negative, and the sequence itself is monotone increasing. Right? They didn't put the word monotone here, but that's the idea for the title. The monotone convergence theorem deals with a monotone increasing sequence of functions. What that means is pick an x value, any x value in set E, and consider the corresponding numbers, f sub 1 of x, f sub 2 of x, f sub 3 of x. That is, plug a specific x value into this sequence of functions. That sequence of numbers is a monotone increasing sequence. That is, the new terms are greater than or equal to the previous terms. It could be constant and it's still considered monotone increasing. If it's constant, it's also monotone decreasing. But this deals with monotone increasing functions. That's the reason it's called a monotone convergence theorem. So if we have pointwise convergence almost everywhere, and this monotonicity condition, then the limit of the integrals is the integral of the limit. The limit of the integral over e of f sub n equals the integral over e of the limit function f over set E. Let's go through proof of this. Some of these proofs are lengthy and not too joyous. This one is one slide. So this is actually easy because we now know a bunch of stuff about this class 2 of functions. Okay, the sequence f sub n is increasing. So the limit is greater than or equal to any of the f sub n's values. That is, f sub n is less than or equal to f. Throughout set E, well, okay, almost everywhere, because we had the almost everywhere pointwise convergence. But I'm going to be really disinterested in sets of measure 0 throughout this integration stuff. But we get f sub n less than or equal to f almost everywhere, so that's established an ordering right there. Monotonicity of integration in this setting for class 2, theorem 4.10 that we proved a while ago, says then the integral over e of f sub n is less than or equal to the integral over e of f. One function greater than or equal to the other, almost everywhere, implies the ordering of the integrals. So there's your monotonicity, and no appeals to bounded functions on sets of finite measure, bounded functions of finite support, none of that stuff in this. We've got monotonicity, so let's use it. Okay, left-hand side depends on n. Right-hand side is just some number. So what you've got is a sequence of numbers on the left and a fixed number on the right. Does the limit of that sequence of numbers exist? I don't know. The lim sup exists. Lim sups always exist. So if we've got this number bounding this sequence of numbers here, the lim sup of the sequence on the left has the same bound. It's also bounded by the integral over e of f. Okay, a little problem with this. I don't want no lim sups, and I want equality. Well, this is totally based on the monotonicity of the sequence of functions. Now let's throw Fotus' lemma at it. Fotus' lemma said the integral over e of f is less than or equal to the lim inf of the integral over e of the f sub n's. So what we've got then is lim sup of the integral of the f sub n's is less than or equal to this, the integral over e of f, which in turn is less than or equal to the lim inf of the same thing, the integral over e of the f sub n's. As you know from your previous analysis experience, lim sups are always greater than or equal to lim infs, if you let me abbreviate it like that. So take that string of inequalities. The lim sup is less than or equal to the number, is less than or equal to the lim inf. Conclude that actually must be equalities throughout, because the lim sup is greater than or equal to the lim inf. The only way you can have both of these holding is when we get an equality. The lim sup equals the lim inf equals that integral over e of f. All three of those are equal. So we can replace lim sup with lim inf, or regular old limit, better yet. And we know that the limit must equal that common value. Were I to give tests on this material, a proof of the monotone convergence theorem is a good one, because it's short. It only requires the monotonicity, and it requires Fotus' lemma, a very standard result. So I like that one because it's pretty straightforward, almost intuitive. Monotone convergence theorem allows us to deal with the integral also of a series of non-negative measurable functions which converge in terms of a series of integrals. The integral of the series is the series of the integrals. In other words, is what we're getting out of this. And this is the first time we've dealt with a series, probably the last time in real analysis 1 that we'll deal with a series, not the last time in analysis, but the last time probably in the Lebesgue stuff. And the statement here is, let U sub n be a sequence of non-negative measurable functions on set E if f is the sum from 1 to infinity of U sub n, pointwise almost everywhere on set E, then the integral over E of f is the sum, the series, sum from 1 to infinity, of the integral over E of the U sub n's. So I've written f as a series, then I can integrate that series term by term, is what this is said. A common kind of expression you'd have from complex analysis is term by term integration, often applied in that setting at least, and in calculus too, to power series. Integrate functions by integrating the power series. Got to make sure you got the right kind of convergence for that to occur in the calculus sequence or the complex sequence. Okay, remember, everything here is non-negative. So when I look at this sequence of functions, if I add up more and more functions, look at the sequence of partial sums, you're adding non-negative stuff, you got yourself a sequence, the partial sums form a sequence which is monotone increasing. So we'll make that observation. Non-negative is giving partial sums which form a monotone increasing sequence, and we'll throw the monotone convergence theorem at it. It is a corollary to the monotone convergence theorem. Okay. Each U sub n is non-negative. So if we'll look at these partial sums, say sum from 1 to k, so k becomes an index here in the partial sums, n equals 1 to k of U sub n. This is an increasing sequence of non-negative measurable functions. Yeah, everything in sight's non-negative and measurable. Add more terms, pointwise, you get the thing to be monotone increasing. So monotone convergence theorem does apply to this. It is an increasing sequence of non-negative measurable functions. Right? The series stuff I write as a sequence of partial sums, and then we're totally having a conversation about sequences of functions as we've had previously, as the monotone convergence addresses. All the convergence theorems address sequences of functions, not series. So this is a fairly unique result for real analysis 1. So the integral over E of f, well, I know f has this representation almost everywhere. So we'll replace f with this representation. Don't freak out about the almost everywhere. Okay, I'm throwing away a set of measure 0. Without loss of generality, I can assume the convergence is everywhere. So I am being a touch informal with that, but it's certainly justified. Just sets of measure 0, they don't affect integrals. A series, actually a series is a limit. It's a limit of a sequence of partial sums. So let's take this series and write it as a limit as k approaches infinity of the kth partial sum. That's just the very definition of a series. Can you bring limits outside of integrals? You can here, because here we've got a monotone increasing sequence of non-negative measurable functions. Here we can apply the monotone convergence theorem. Yeah, I can bring limits outside of integrals if I have a convergence theorem, because this is an increasing sequence, a monotone increasing sequence. Monotone convergence theorem applies. So I can bring the limit outside of the integral, okay, one little step at a time. Now we've got an integral of a sum. Now we've got an integral of a sum. Well, integral of the sum is the sum of the integrals by linearity. The U sub n's are what? Non-negative? We've got a linearity result for that, as proved in this section. The linearity and monotonicity. So we're good. We've got we got linearity covered. It's finite sum. That's the reason we had to take that infinity symbol outside of the integral. Linearity doesn't say the integral of a series is a series of the integrals. I guess sometimes it is because that's what we're proving here. But in general, linearity only addresses finite sums. When you hear the word linear in linear algebra, it's always finite sums. It's never series. Series become a much more complicated thing. You worry about divergence if you add an infinite number of things together. So anyhow, linearity deals with finite sums, so we're good. We got a finite sum here. And here we are again. You got a limit of a sequence of numbers. The limit of a sequence of partial sums is a series itself. So by definition of series, that becomes the sum from 1 to infinity integral over e of u sub n, and that's what we claimed. So that one actually is fairly straightforward, totally unsurprising in light of the monotone convergence theorem. Okay, another definition. We're going to use the word integrable in a different way. In the past, when we use the term integrable, such as Riemann integrable or Lebesgue integrable, it dealt with the existence of an integral, usually in terms of equality of upper and lower integrals. It did for Riemann. Riemann integrable means the lower Riemann integral equals the upper Riemann integral. Lebesgue integrable in the setting of class 1 functions, bounded functions on sets of finite measure. Integrable meant the upper Lebesgue integral equals the lower Lebesgue integral. Here we're using the term integrable in a different way. Here we're using the term integrable to deal with the finiteness of the value of an integral. Here, we could really care less. Integrals can be infinite. Integrals can be infinite in calculus too. I don't mind having infinite integrals. We're not doing this for class 2. We're doing this for class 3 of functions. This finiteness of certain integrals, we'll use it in the next section, because if we've got infiniteness and we've got subtraction, we better keep our eyes open for any infinity minus infinity situations that might arise. So the following definition involves the word integrable in a new setting. So beware, this is an unfortunate choice of terminology in my opinion, because it reminds me of something else. We've used this term in other settings. And the motivation for this is not entirely relevant to this section. We're doing this now because it applies to non-negative measurable functions, the functions we're talking about in this section. But the real application of this definition will be in the next section. A non-negative measurable function f on a measurable set E is said to be integrable over E if the integral over E of f is finite. So integrable means finite integral. In this setting, non-negative measurable functions are integrable when the integral is finite. And we could certainly come up with plenty of non-negative measurable functions that have infinite integrals. Not hard at all. Take an exponential function over the reals. Not surprisingly, the integrability of f implies some kind of finiteness of function f. Consider the following. Let non-negative function f be integrable over e, that is, the integral of f over e is finite. The claim is f is finite almost everywhere on e. Sounds fairly plausible. Let's look at a proof of that. Okay, integrable, finite almost everywhere. All right, let n be a natural number by monotonicity of measure. It's been a while since we talked about that. And Chebyshev's inequality, we get the following. So another application of Chebyshev, the measure of the set of x values where f of x equals infinity, claim is that's less than or equal to the measure of the set of x values such that f of x is greater than or equal to n being a natural number. Sure, if f of x equals infinity, and I interpret infinity as being greater than or equal to n for all n. It's a little oddball to deal with inequalities with the infinity symbol, but we're doing it with the extended real numbers. So any points in this set are in these sets for all n. Also, there may be some places where f of x is finite, yet still greater than or equal to n. So there's points over here that may not be in this set. This is a subset of that set, in other words. So the measure of the set on the left is less than or equal to the measure of the set on the right. Monotonicity of measure from back when we began measure. Lebesgue said the measure of x values satisfying this type of inequality was less than or equal to 1 over this number, 1 over lambda we had, but 1 over this number, n in our case, times the integral of the function. All right, so what we've got of interest is the measure of the set of x values on which x takes on the value, f of x takes on the value infinity, is less than or equal to 1 over n times the integral over e of f. The integral over e of f, that's finite. F is integrable. So that integral is a finite number. N could have been any natural number. So think of it as we can make n large. When n becomes large, this term can be made small, smaller without bound, well, smaller bounded by 0, but arbitrarily small. And so the measure of the set on the left, that must be 0. This quantity must be 0, bounded below by 0, of course. And the measure of the set of x values where f of x equals infinity must be 0. In other words, this function is almost everywhere not infinite. That is, it's finite almost everywhere. And not a surprising result. One final result. I don't think this was in the previous editions of the books. I don't think. It might have been. It deserves to be called a convergence theorem, I would say. It's called Lebesgue's Lemma. It says, let f sub n be an increasing sequence of non-negative measurable functions on f if the sequence of numbers, the integral over e of f sub n, is bounded, then f sub n converges pointwise on e to a measurable function f. It's finite almost everywhere, and the limit of the integrals is the integral of the limit, and that function is integrable. This sequence of integrals is bounded. That's a new thing. That's the thing they put the bound on. So what we've imposed is kind of a uniform boundedness on the integrals themselves of the functions, the f sub n's. So that's the thing they put a bound on. And that gives us a convergence theorem type thing. All right, let's go through the proof of that. So that's just a few lines, so that's good. And this is our last result for this section. Okay, increasing sequence, they mean monotone increasing. So we got the monotone convergence theorem working for us. Every monotone sequence of extended real numbers converges to an extended real number. So monotone increasing sequence either levels off at some value or doesn't, and it diverges to infinity, how you describe it in calculus. So that's what's being said here. So f sub n converges pointwise on e to some function f. That limit function is measurable. Pointwise limit of a sequence of measurable functions is measurable. Proposition 3.8 when we were talking measurable functions back in chapter 3. Monotone convergence theorem tells us the sequence of integrals approaches the integral of the limit. Limit of this sequence is the integral of the limit. The limit function is the function f. Since these are bounded, then its limit's got to be finite. That is, the integral over e of f must be finite. The limit on the right's finite. All these things are bounded by the same thing. Call it capital M. So this thing here, their limit value is also bounded by capital M. So that gives us the finiteness of the integral. Knowing the integral is finite, we just observe proposition 4.13 that being integrable implies the function f must be finite almost everywhere on set E, and that was the final claim there. So there's Lebesgue's lemma. It's pretty much a convergence theorem as well. And that takes care of class 2 of functions, non-negative functions. So what's left in terms of developing Lebesgue integration is section 4.4, and there we'll consider integrable functions. We'll allow functions to be both positive and negative, leading to concerns about infinity minus infinity, but the integrable we introduced here, that'll come to the rescue in that class of functions. So that's where we use the integrable part by looking at positive and negative parts of functions and requiring those to have finite integrals, thus avoiding infinity minus infinity. So what will totally drive the next section is an avoidance of infinity minus infinity in terms of computations. So we get that out of the way, then we will have developed Lebesgue integration. So I will see you in class 3 of functions here in the next video. Have a nice day.